Have you ever wondered why two storms with the same rainfall depth can produce completely different floods? In this video, we run a sensitivity analysis using the RORB, a hydrological model, testing how changes in catchment features like slope, shape, imperviousness, and even rainfall temporal patterns transform the flood response. From time to peak to runoff volume and peak flow, you will see how small changes in the catchment can mean the difference between minor flooding and major disaster. Catchment hydrology is a complex interplay of factors. Runoff isn't just about rainfall. It's the outcome of how catchment shape, slope, soil type, and land cover interact with each storm. Changing even one variable can alter not only the runoff volume and peak flow, but also how quickly water reaches the outlet. Due to this complexity, simple formulas often fall short. We need models to isolate and quantify the impact of individual parameters on key outputs such as time to peak, peak flow, and total runoff volume, while keeping other variables constant. In this tutorial, we will use RORB, an abbreviation for runoff routing over basins, a conceptual rainfall runoff model widely applied across Australia for flood estimation and drainage design. RORB represents a catchment as a system of interconnected, nonlinear storages, simulating how floodwaters move and delay through the landscape and stream network. It's an ideal tool for systematically exploring how factors like catchment shape or rainfall temporal patterns influence catchment response. Our study catchment is a hypothetical basin located in southeast Melbourne. It covers an area of approximately 4 square kilometers, extending 3.5 kilometers from north to south, where the outlet is situated. The catchment has a uniform slope of 0.4%, gently descending toward the outlet. To minimize any unintended influence of geometry on the results, the catchment is designed to be symmetrical along a vertical axis passing through the outlet. Representing a low-density residential area, the catchment has a uniform fraction impervious of 0.2. It is divided into 6 subcatchments evenly distributed on the eastern and western sides. The design rainfall event used for this analysis is a 1% AEP storm with a duration of 60 minutes and a depth of 44.7 mm. Our baseline rainfall losses are assumed to be initial loss of 10 mm and continuing loss of 1.5 mm per hour. Our catchment is implemented in RORB with the following details. It includes 6 sub-area nodes representing the 6 subcatchments. It has 4 joint nodes which are connected by 9 reaches. All the reaches are assumed to be of type 2, excavated but unlined. It is also worth noting that in this analysis we only focus on the model results at the catchment outlet, as indicated by the red color. First, we start with the impact of rainfall temporal patterns, or TPs, on catchment response. As you may know, guidelines recommend TPs for different rainfall durations and frequencies based on the historical data records. For example, Australian Rainfall and Runoff guidelines offer 10 TPs for each specific rainfall duration and frequency based on the recorded rainfall events in the country. This is provided in the AR&R data hub. However, in this sensitivity analysis, we will not use the data hub TPs. Instead, we use 5 distinct temporal patterns representing typical rainfall distribution scenarios as follows. TP1 is uniform rain. This will work as our baseline for comparisons. TP2 is intermediary or center-loaded storm, where the greatest amount of rainfall or the highest peak intensity is concentrated around the midpoint of the storm's total duration. TP3, front-loaded storm, is representing the case that the highest intensity and greatest volume of rainfall occur in the early part or the front part of the storm's total duration. TP4 is back-loaded storm, where the highest intensity occurs in the later part or the back part of the storm. Finally, TP5, bimodal storm, also known as double peak events, where 2 distinct peaks are exhibited in the storm, one at the front and one at the back. Well, let's run the model. I've already uploaded the file, so I click on the run. I've chosen the separate catchment and generated design storm. It's on the AR&R 2016 data, and then I click OK. And then in the next page, I've already uploaded the ARF, which is the area reduction factor information, as a text file. I've downloaded it from AR&R data hub for the site. And then the second tab is for the temporal patterns. The 5 cases that we just presented in the previous slides are provided here. And then in the next one, we provide the IFD data, which is again downloaded from the AR&R data hub. I go for the ensemble simulation. I choose 1% AEP. The reason that I choose ensemble because I want to have all TPs being run at the same time. And then our duration is set for 1 hour as we decided about that. In this tutorial, I ignore the pre-burst and also embedded burst because it's a kind of hypothetical catchment and rainfall events that we are using. And at the end, I choose where the results basically are going to be provided. I click on OK. Then the next tab come up. I need to set the routing parameters. M is recommended to be 0.8 for the KC. Generally in Victoria, we go for this item, which is the Pierce et al. Formula. And that one suggests 3.02. This is one of the routing parameters. I adopt it. And then I need to manually enter the loss values. If you remember, we decided to have initial loss of 10 and continuing loss of 1.5 mm per hour. I click on text and the model run. It's quite fast and I get the results. So I need to now go and compile the results and show you the outcome of this sensitivity analysis. Well, the compiled results of the sensitivity analysis on the 5 temporal patterns that we had are presented here in terms of a hydrograph and also a table which summarizes the values of the catchment response. So if we look at the time to peak, as it is expected, the front-loaded or TP3 give us the lowest time to peak of 0.83 hour. And then the longest one obviously goes to the backloaded and also the double peak with 1.25 hour. And then if we look at the peak of the runoff, the lowest again goes to the front loaded. And the reason of that is the major chunk of the rainfall in this TP happens at the front. And that's exactly where the initial loss is also active. And because with a big chunk of the rainfall at that stage of the event will be consumed by the initial loss. And as you can see, the impact of it is significant and the runoff peak at TP3 and also the runoff volume at the same TP is the lowest. And obviously the opposite condition is going to happen for the backloaded event. As you can see, the highest peak of 37.7 happens at backloaded because of that same reason. Because initial loss is not consuming much of this rainfall event. And of course, the runoff volume will be slightly higher than the others. It is also worth noting that the uniform and the center loaded events are generally quite similar to each other when it comes to the runoff volume. But if we compare the time to peak and the runoff peak, the center loaded event TP2 is going to have a higher peak and also a faster time to peak. Next, we explore the impact of increasing rainfall loss on catchment response. In this tutorial, we only focus on the initial loss, as changing the continuing loss may not have a significant impact on catchment response time. In this process, we increase the IL from 10 mm to 20 mm and we run the model over the same 5 temporal patterns. Well, after increasing the initial loss and running the model, the results are compiled here in terms of a hydrograph and also the tabulation of the time to peak, runoff peak, and runoff volume. I've also provided the baseline values, means what we did in the previous step, to have a comparison between the increased initial loss scenario versus the baseline. So first I look at the time to peak. As you can see, there is no major change in time to peak except for TP3, the front-loaded one, since we are losing more on the rainfall at the beginning of the event. The time to peak has been decreased because I think less amount of water is there, less runoff is available, and automatically everything related to TP3, including runoff volume and also peak flow, has been reduced, and time to peak obviously increases, means has a delay basically compared to the previous one. When we go to the peak runoff, we can see that compared to the baseline scenario, all the numbers are relatively between 22 to 25% lesser, and that's because of losing water to initial loss. When we come to the runoff volume, we have a kind of 25% drop of volume in all TPs. There is no much of difference, except as usual, the front-loaded one is affected more compared to the others, while the back-loaded one is less affected because of having the rain at the back of the event. To explore the impact of catchment shape, slope, and imperviousness on catchment response, we focus on our baseline IL and CL values and only investigate the center-loaded temporal pattern, or TP2. First, let's change the catchment shape by elongating it. In this change, we keep the catchment area fixed while the catchment length increases from 3.5 to 4.5 kilometers. This change will increase the length of the reaches in the model. Well, for the elongation case, we increased the length of our catchment by roughly 30%, as you saw. And now we see the results of that on the hydrograph and also a summary table that compares the values, numerical values of catchment response. As it is expected, by elongating the catchment, time to peak will increase from 108 to 1.17, and because of a longer pathway, the routing effects will actually reduce the runoff peak from 34.57 to 26.38, which is a relatively significant drop. The runoff volume, of course, it's not going to change, and the reason is that in our comparisons here, both baseline and elongated scenarios having the same rainfall event and also same losses, so it's not expected to be different. And since we are using the same TP, by right the same runoff volume should come out, and you can see it is happening here. Now let's change the catchment slope. For this, we refer to the original catchment shape and increase the slope from 0.4% to 0.6% while keeping all other variables constant. In order to implement the steeper catchment in our model, what I'm going to do is to click on each reach, so like this, and then I manually increase the slope from 0.4 to 0.6, which is the targeted slope in this sensitivity test. And I click OK. And I need to do the same thing for every reach. And after completing that, I will run my model similar to the other cases that we had. So no changes in the parameters. To save time, I just directly go to the results. As you can see, the hydrograph shows that we get a faster runoff. So the time to peak decreases from 1.08 to 1 hour. And then when it comes to the runoff peak, of course, a steeper catchment generates basically a faster flow or more flows running to the outlet. And that's why we see a slight increase in the peak runoff from 34.57 to 37.97. As we discussed in the previous case, the runoff volume doesn't change because the same amount of rain and same losses are applicable in this comparison. Finally, we change the fraction impervious. For this, we work with the original catchment shape and slope and only change the fraction impervious from 0.2 to 0.4. In order to implement the case of larger fraction impervious, what I'm going to do is to click on the catchment nodes or sub-catchment nodes like this, and then I will manually increase the fraction impervious from 0.2 to 0.4 and then click OK. I need to do the same thing for all the catchment nodes manually, and then once done, I will be ready to run my model with the same parameters as before. Again, to save time, I just skip the process and directly go to the results that I've prepared earlier. As it is expected, we get a smaller time to peak, means the catchment response will be faster. If you look at the time, and then the peak runoff obviously will be larger. And of course, this round we will get a larger runoff volume because we have increased the imperviousness, so less amount of water infiltrates to the soil. And because of that, we will get more excess rainfall and obviously more runoff volume. As we saw in this tutorial, catchment response is incredibly sensitive. Even small changes in catchment or rainfall characteristics can completely reshape the hydrograph. This is where hydrological modeling helps us understand how a catchment behaves under different conditions. In our next video, we explore how to determine the critical design rainfall for a catchment using RORB, a hydrological model. This will help us to identify the storm that produces the maximum flood response. It's a crucial step in flood estimation and drainage design, so stay tuned.